So don't make fun of me if I get this one wrong, but actually I'm gonna click solve just in case. What this next section is about. This is sampling distributions, and this is the way we mostly do statistics. The problem that we were just doing said what is the proportion or what's the probability that we randomly pick one and they are less than 72 inches tall. Okay, what's probably like that very first problem it did, it said what's the proportion that you pick one person and they're less than 72 inches tall. Okay, that one woman's height, like what is that one woman's height, what is her score going to be? What really happens though is like if we are, I got my water bottle right here, so this water bottle is 16.9 ounces, 500 milliliters, right? So there's somebody at this water bottle factory that measures this water bottle, okay? So they probably produce 1 million of these a day or something like that. I don't know how many plastic water bottles they make, but let's say 1 million a day. Well, if they just pick one water bottle to test to see if it's about 500 milliliters, maybe some are $4.99, maybe some are $5.01. That's not that big of a deal, right? But you don't want that one that's like $4.90. You don't want it to be too far from 500. But if I pick 1 million of water bottles a day and I only pick one of them, that doesn't give me very good numbers to work with because I'm picking one out of 1 million, right? Well, let's pick 25 of them throughout the day, okay? And I'll take the average of those 25 and use that average to run my numbers, okay? Does that kind of make more sense? So what we just did, you pick one. What this section is all about is you picking more than one. You pick 25 water bottles. You pick, the Budweiser factory. You're going to pick a 6-pack or whatever. Like you pick something like that. You pick a certain amount of that's more than one, and it's called a sampling distribution because you're picking a sample out and you're looking at that average of that sample compared to the rest of them. So what this tells you right here is that the more and more numbers you pick, the closer and closer you're going to get to that picture, okay? So the first top picture right here is my correct answer. The population mean is 1.5. I don't even pay attention to that really. What this is going to say, actually I do need that. Sorry, this is a new topic, so I'm still learning it too. So my mean is 1.5. So I have this graph right here and I got to choose one of these three. I am choosing which one of these graphs has a mean of about 1.5, okay? So like this one, the mean is going to be like 2.5 because you see where those high graphs are. This one, the mean is going to be like 0.5. This one, the mean would be about 1.5, okay? Same thing on this one. I'm trying to pick the one that has the mean of about 1.5. So the one that looks like the middle is about 1.5 would be that one right there. The more and more sampling I do, the closer and closer it gets to that normal curve. And that is what this topic is showing you. So on this one, again, the same thing. I am picking the graph that has a mean of 1.5. All right, okay, so the middle of these graphs at 0.9 or 1.5 or 2.1. So you pick the one that has the mean, the 1.5. That's all you have to do on this. But what it's showing you, and this is what you're supposed to recognize, it is showing you that, oh no, can I not get, I'm just going to, it is showing you that the more and more that you sample, the more and more times you do it, the more and more it gets to be like that normal bell curve, which really helps us, okay? So I'm just going to write this real quick. From above, the mean is equal to 1.5. So you try to get the mean equal 1.5. Mean equal 1.5. Mean equal 1.5. Okay. So that's all you got to do is try to match those means up on there. That topic should just take a second. Now, again, it's an easy topic, but don't forget the idea of what you're doing there. What you're actually doing is showing that it turns into that normal curve the more and more you ask it. All right. So if we are going to compare, if we're going to, randomly pick 6 water bottles and compare them to how it fits, I'm doing the average of those 6 water bottles. So what that really affects, I don't really care about my average. My average of the 6 water bottles should still be around 500 milliliters, right? Because that's what we're trying to fill in the water bottle. So my average is not going to change at all. But my standard deviation is going to change because I'm looking at the average of 6 water bottles compared to all of them instead of the average of 1 water bottle compared to all of them. So topic is actually super easy. And this is the only thing that we have to do that's different than the last section actually is that when you are doing sampling distributions, so this is the symbols that they use. They're saying you're finding the mean of the sample, okay? The mean of the sample average, or the standard deviation of the sample average, okay? When you find this one, this is kind of strange, but this is actually equal to your mean, okay? The mean's not going to change. It's always 500. I'm still comparing it to 500. The mean does not change. But my standard deviation is going to change. And I do the standard deviation. This is the formula. You probably write this down. Standard deviation divided by the square root of n. Okay? So on this problem, my mean is 3.9. So that's just 3.9. My standard deviation is 0.8. And we're sampling 10 tires. I don't have time to sample all the tires, but I don't want to just sample one tire, so let's just sample 10 to see how they fit or whatever we're doing here. So I do 0.88 divided by the square root of 10. Okay. So here is the trick here. I know I've said a lot of things here, but divided by square root of 10 should be about 0.278. Here's what I know, or the way that I know this. And when you mix all these problems together, when you are sampling more than one, I'll write more than one, you change your standard deviation, okay? Your mean's not going to change because all my water bottles should be around 500 milliliters, but your standard deviation is going to change, and you use this formula right here, okay? The standard deviation divided by the square root. Everything else is exactly the same as what we just did. Come on. So the central limit theorem. My iPad has not been loading today. Let's see if we can get this. Okay, so alcohol withdrawals occur when a person uses alcohol excessively, suddenly stops alcohol use. Studies have shown that the onset of withdrawals experience a mean of 40 hours and a standard deviation of 18. A sample of 35 people who usually use alcohol excessive to be taken. What is the probability that the sample mean time of the last drink onset will be 38 hours or less? Okay, same button, 38 hours or less. So we do the z-score, 38 minus the mean, which is 40. Here's where things get a little different. I am sampling 35 people, right? So I'm going to change my standard deviation. I don't want to just sample one person because there's too many variables in a human body, right? So I'm going to sample 35 and see what happens. So what I do is as soon as you see a sample of 35 people, change the standard deviation so you can go off in your brain. So I'm going to do the standard deviation divided by the square root of n, which is 35 people. We sampled 35. That's the only thing I do different is change that standard deviation, okay? Then we go back through our same other steps. It's 38 hours or less, right? So I shouldn't have to change the sign. I could do less than or equal to. So this should be my answer. All you have to do is change your standard deviation when you are doing these problems. So it is the same idea of what we just did. That's why I wanted to go ahead and do it real quick. Sample 35. That tells us to change our standard deviation. So the formula you are actually using is x minus the mean divided by the standard deviation divided by the square root of n. Okay, you will see this formula again. This formula pops up a few times. The other thing that we got to make sure we pay attention to is, remember, what's our mean? 40. We're doing 38 or less. So it is to the left. We're good there, okay? Another thing about drawing this picture out real quick, doesn't this look, just with a quick sketch, doesn't that look like about 25% of that thing's covered? That helps you check your answer when you do something like that, okay? All right. So that is the exact same thing as what we were just doing. Again, all you have to do is change your standard deviation. Do the standard deviation divided by the square root of n. 2 more topics and we're done. This one's super easy. Oh no, it's gonna mess with my brain though. We'll make a chart real quick. But this is talking about the difference between a population proportion and a sample proportion. Okay. So the population proportion is the one that we actually, we read an article and saw this number, or maybe it happened before COVID and we want to know what it's like after COVID. So the population is, again, the entire group. So let's say at the last home match, 25 out of every 56 attendees were children. So what is 25 divided by 56? 25 divided by 56 is 45. So 25 out of 56 is going to be my population because it says every. At the last home match, okay. And then it says he found 43 out of 89 in a sample. Okay, so this one would be 43 out of 89. We'll double check that. 43 divided by 89 is 48, okay? So you have to figure out when to use population, when to use sample. They should say it pretty clearly in the problem. The symbols, though, you will run into these symbols. There are a few different symbols. And we'll go ahead and make a list right here. You might have seen this before. The population and sample. So the first one is proportion. And honestly, this is the one I always get mixed up. But you are going to do a population is just the P, and a sample is the P hat. The way I remember that is the hat is always a prediction. Like we just do a small sample, try to predict for the entire population. Okay. So the hat is the sample proportion. I don't know what else ones you'll see, but the mean, the population is the mu and the X bar. The standard deviation, they use they always use Greek letters for those. So Greek letters, the little sigma, and then it's S for sample. I thought there was some more I had in here. What else we got here? I think those are the only ones they'll use. I know y'all are just watching my iPad to see if it's going to die before we get done. I only got one more topic. Okay, that should be the only symbols they use on this one. Maybe I was thinking of a different topic that I had those other ones. So really this is just going to be the P hat or the P. The P hat is a sample, the P is a proportion, and then you just got to read the problem to see there. All right, as I die real quick here, once the iPad dies, we'll try to do this last one. The last thing, so everything we've talked about so far is like mean and standard deviation. You can do this with proportions. So the proportion, when you're doing a sample, right, this one we are sampling 7 scratchers and seeing how often they win. That's more than one. So as soon as it's more than one, you're thinking I got to change the standard deviation. The mean stays the same. So my mean proportion is going to stay the same as the mean, 42 right there. That stays the same. My standard deviation one, though, I do this formula, P times 1 minus P over N. It's a little bit of an annoying formula, but there's nothing I can do about that. This is like the one worst formula. I think I told you at the beginning of the semester, there's one formula that doesn't have on the calculator that you got to do a couple times is this one. It's not nearly as bad as it seems, though. Okay? If 42% of my scratchers win, what percent loses? I know, that's hard math. 58, right? That's all that's saying. That's what that 1 minus P is. Now, you can do that in the Alex calculator. I'll show you in just a second. But it's 42 and 58. Those numbers always add up to be 100%. And then I divide it by my sample, 7, and I get my answer. Okay? This should equal 0.19. So that's all you got to do on this topic is change that standard deviation because you are sampling more than one. And the way you find a standard deviation of a proportion, this is how you find the standard deviation of a proportion. You are going to use this formula right here. So all this is, this section that this one doesn't start next week for y'all, but all this section is an extension of what we did this week. And when you say you sample more than one, you've got to change the standard deviation with one of those formulas. Just to double check to make sure I did that right. You can do 0.42 times parentheses 1 minus 0.42, which is 0.58, and then divided by 7. Okay? You are allowed to do that. That is fine. I just did 0.42 times 0.58 in mine, but that works either way. So if it ever says, when you mix all these together on the test, this is where it gets hard, and we'll definitely do that on review day, but anytime you sample more than one, you have to change the standard deviation.